Puts it down.
A little bit.
Yeah.
You should
Well,
check out the ones that
the no wheels on the back means they don't.
So it's like
I
sitting at the
have to
art
use
town.
them. They look really fancy.
Check those out. I have like 3 rooms on my campus, so there's more left to see.
Somehow I always get in the same room. 6 semesters down and I'm in the same 4 rooms.
Okay, so let's get rolling, guys. First off, this is last class's slides. I just want to go through what we talked about. This is Tycho Brahe and this metal nose. It was always said that his nose was either silver or gold. By the way, they exhumed his body not that long ago, and they found traces of copper right around his face. So he may have had like a brass or copper nose instead. I can picture having like your everyday brass nose and then having like a special silver nose for special occasions.
We want to wear it all the time against stuff.
Yeah, that's true. So we like, no, like he did carry a sword. So we got to the point where we were talking about him becoming the imperial mathematician to the Holy Roman Emperor Rudolf in Prague. And there he's joined by Johannes Kepler. And they became just an amazing team because Brahe was a practical astronomer. He was really good at making measurements and doing observations, but he didn't have the greatest math jobs, which is surprising that he got, appointed the imperial mathematician to the Holy Roman Emperor. But Kepler really was good at math. So there's Kepler. His nose is completely intact.
That's a nose someone could be proud of.
That is a good looking nose, isn't it? I think he's a handsome gentleman. I'm not going to get too into that one. I don't like. So what is Kepler famous for now? He took Tycho Brahe's data, in particular his data about Mars, because he had years and years of observational data about all the planets, but Mars was the best data in terms of, Mars is the one the planet that's probably easiest to observe. You never mess up and think Mars is a star. Because there's only one star in the visible star in the sky that's as red as Mars is. And that's in Orion. It's very prominent. You're not going to think, okay, you're not going to mix Mars up with something else. I guess Jupiter is pretty clear too. Right? Jupiter's orbit is, but Mars is a little more elliptical orbit than Jupiter, so the deviations from circular orbit are more clearer on Mars. And that's the big thing that he came out with finally. After just looking at the data and not having preconceived notions about, God would only have circular orbits, he said, well, I know what this curve is. It's an ellipse. And then he checked, and all the other planets seem to be following elliptical orbits too. So that's the first law of planetary motion. Which is this right? Probability. Oh, okay.
It's exam 2 on Monday in chapters 11 and 12.
Not in this class. So the planets move in elliptical orbits, and an ellipse has a couple of special points on it that are called the foci. So if you have never done this before, I demand that you go home and try this. You must go home. You have to go home and do it. What you do is you put 2 tacks down in a board, or use nails or something. But it's got to be shoved in so that it's not going to budge. And you take a loop of string and you put it around those tacks, and then you pull it tight by sticking a pencil into the loop and pulling off to the edge. So once you've done what I've just described physically, the string will be tight like this and come to a point, and your pencil point is right there. And now holding your pencil point, holding tension in that cord, you start moving your pencil point, and it draws an ellipse. It's really fun. I bet we could find a YouTube video of somebody drawing an ellipse with string and tacks. Okay. But these points, actually my ellipse is really kind of eggy, isn't it?
You get the idea.
Well, you get the idea. These points are sort of the same distance in from both ends, and that's probably more like it. And those are called the foci. one focus and that's the other focus, but collectively they're called foci. The way the planet's orbits work is the sun is one of the foci. And what's the other foci? What is those? I've never heard a good explanation of what's hanging around at the inner focus.
How far away is it from the sun?
Winter solstice?
It's probably inside the sun for most of the planets, except for Pluto.
Winter solstice? Summer solstice?
So the solstices have to do with the inclination of the planet.
Wow.
Like, the Earth is inclined about 23 degrees to the plane of its orbit. So in the summer, we're actually farther from the sun. Did you know that? It's a weird thing. It's true. The northern hemisphere summer is when the northern hemisphere happens to be more pointed at the sun, but the planet is actually farther away from the sun at that time.
So the summer down south, well, the winter down south has to be really hot.
Well, they call it summer. But
They call it summer?
they call it summer. When it's our winter, it's their summer. But they still call it summer when it's hot. Yeah, the Australian summers are hotter than the summers here. And,
Well, it's only the temperate region of South America that actually is in the winter.
One of the things that is problematic about our planet is the distribution of land and ocean. And if you look at the southern hemisphere, it really doesn't have that much land in it. It's got Africa, which is one of the biggest continents, right? But
Well, like
only half of it. You know, the equator cuts through. If you notice how the Africa kind of looks like a human skull, the equator is loaded right there. So this is the only part that's below the equator. Australia is out over here somewhere. And then there's a bit of South America that sticks down below the equator. That's kind of pointy. Ice cream cone. But anyway, there's a lot less land in the southern hemisphere than there is in the northern hemisphere for people to live on. I don't know. Where was I going with that? Just that.
how it regulates the seasons.
Well, yeah, I guess it's about the seasons because the sun that's coming down when the southern hemisphere is more pointed out towards the sun, giving you summer in the southern hemisphere, the portion of the planet that's pointing at it is not as absorptive of light. It's called the albedo of the thing. The northern hemisphere has a lot of land or ocean. It's a pretty good reflector. And so that sunlight comes in and just gets reflected off for the most part in the supposedly hotter summer in the southern hemisphere. If we had both things reversed, if the world was actually turned on its head and the northern hemisphere was down here, and so it was closer to the sun, we'd have a huge difference. But because of the distribution of land, the difference isn't as large. I guess that's what I was saying. What we really were supposed to be talking about is Kepler. His first law was planets move in elliptical orbits about the sun. For most of the ellipses that we're talking about, the distance between these foci isn't very large. I mean, the Earth's orbit is 93 billion miles in radius. 92 million, sometimes 93 others. The distance between the foci is probably about 2 million miles. Because the eccentricity of the Earth's orbit isn't huge. It's about 98%. Still, it makes a difference. Definitely, you can tell that the Earth is sometimes farther from the sun and sometimes closer. Okay, so that's law one. I took several years of examining the observational data that Tycho had come up with, and he finally realized this. So this is the Copernican system, but with the Kepler's modification. So I mentioned Copernicus before. We didn't actually talk about him too much. But Copernicus is the first guy who said, no, the Earth can't be at the center. It's got to be the sun that's at the center, and all the planets are going around it. That simplifies a lot of things. The biggest problem with the Copernican system is parallax. If the Earth is moving, we should be seeing the stars from different angles at different points in our orbit, and we aren't able to detect that motion, that parallax motion. I mentioned this when we talked about It's iconic thing, wrong for bright reasons, exactly. So the real issue is nobody could imagine that God had painted the stars on a globe that was 4 trillion miles away from us. And it's really, light years are long, and the closest star is 4 light years. It's an unimaginable distance. Well, I guess it's imaginable. I mean, I can't get a good grip on it. Like, the fastest man-made object of all time. You know what the fastest man-made object ever is?
Voyager 2.
Yeah, one of the Voyager probes is slightly ahead of the other one, so it's actually Voyager. You're right, Voyager 2 is one. It's catching up and getting ready to pass us. It's the one that's launched first. They're leaving the solar system now at about 1% of the speed of light. That means they would take 400 years to get to the closest star. And that's the fastest thing we've ever made. 1% of the speed of light. Yeah, it's nothing. Yes.
Like, I used to use financing a project to actually get us to Alpha Centauri
Yeah.
much faster. The problem with Voyager is it's mass. So rather than sending massive satellites, you're sending a whole army of tiny satellites.
Tiny satellites, or tiny. Yeah. Well, so there's the potential to take a very, very small probe and launch it with incredibly high accelerations at first, and then just let it drift. So essentially, you cannon. You could do something like that. There's also been a good option is to use a solar sail. So you have like a thin mylar film that you can spread out maybe several miles across, and it catches the sun's wind, and so you can literally sail on that. But the problem is once you get out past around Neptune, the wind is kind of slow. It's dying out, right? So the next phase is to build a giant freaking laser and point your laser at the probe that's going out with its solar sail extended and kind of boost it the rest of the time.
Yeah. Humans are awesome, or we have the potential to be.
We have done some amazing things. I think we should be proud of the fact that our civilization sent a probe to Pluto. We've got pictures of Pluto. Great. We should be proud of ourselves. Anyway, hell, I'm proud of this guy just figuring out that the planets were in ellipses. This was from naked eye observations, right? I mean, they were very careful, good observations, but still done with just eyeballs. He was able to figure out, and you know, like I said, these ellipses aren't very elliptical. They're really close to being circles, so that he detected the deviation from the circle is quite a big deal. Well, he wasn't done. After another, it was 10 years, he nailed down how they would run those ellipses. And so for that, I'm going to draw a very exaggerated picture of an orbit. There's a very elliptical orbit. The sun would be done right here. If you're in an orbit like this, when you're close to the sun, you're moving rather fast. So I'm going to try to draw velocity vectors on here in a couple of places. But as you leave this vicinity of the sun, you're sort of going uphill. You're fighting the gravity pull of the sun. So you slow down. So you might be half as long here. And when you get out here, you're going really quite slow. You still got some motion, or you wouldn't be kind of going sideways. Then on the way back in, you speed up. You expect this. So you get up to speed rate. This first vector should have been even longer. So here's what Kepler figured out from that stuff. And I think this, well, interesting. He did not know about the way I just explained it, that the sun was pulling on the planets. That's Newton, which we'll talk about next week. Newton said that the force of gravity had to do with things just attracting one another based on their masses and how far apart they are. Right? So he didn't know there was an attractive force here. He was just looking at the data. So well, Mars seems to be going in and out, and realized he had an ellipse there. And he was able to figure out velocities along these ellipses by comparing your position from one day to the next. Right? So that. So he had this notion of velocity. What could he do with this? He finally realized that if he drew a line from the sun out to a body that's orbiting, and then clicked off a certain amount of time, maybe 1 day or 2 days, maybe a week. A week later, It's in a new place. But if you did that same kind of line from where we are today, time 0 and time 1 week, if you did that same calculation or that same picture when it was close to the sun, it would look more like this. Because you're going a lot faster when you're right here. So that's 0 and this is 1 week. And finally, insight hit him that what the connection between these two things are is they have the same area. This area and this area are equal. So that's Kepler's second law. The line from the sun to the planets sweeps out equal area in equal times. Have you run into that law before? Have you heard of Kepler's three laws? This was pretty important to know.
M1 plus M2 times P squared equals KAQ.
If you've done this in Calc 3, there's a really nice way to see this connection by doing vector cross products, and I think that's the calculation. That's the output of it. That wherever you are, when you calculate a particular vector cross product that gives you the area of this thing, it's going to come out the same.
Actually, that was the formula of the third law. That was the formula of the third law.
Oh, okay. The third law. Oh, we're not there yet. So what's the third law? That's the one I always forget. It's about the total period and essentially the average size of this orbit. So let me first put those things in. What is a period of an orbit?
Time it takes to cover 100.
It's the full revolution. So for the Earth, it's 1 year. That's easy. Actually, maybe it's not. It's 365 and a quarter days plus a little ish, right? Because that's why we have leap years. And then every 100 years we have non-leap years, even though it should be a leap year. We just have one of those.
Unless it's a 400 year.
Unless it's a 400 year. Now what we're talking about, this is called the Gregorian reform. They finally figured out how to fix the calendar so that it didn't keep falling out of sync.
And we're good at like the year 10,000 or something.
Oh yeah, well, I mean, there's actually extra stuff. Like the scientists occasionally add leap seconds to it when you're just to keep things even nicer. Did you know about leap seconds? Amy looked like, no, I don't believe that. They did. They just say, okay, we got to put an extra second in 2019 because things are getting off. Anyway, yeah. So, what would you use as kind of the radius for this thing? For an ellipse?
Very similar.
Well, there is a middle to the thing. It's not at the focus, and it's actually kind of halfway between the maximum and halfway and the minimum. And then side to side, it's easier. It's right in there. There's like a centroid for the area. And from here you have two ideas of radius. One is to go out to here, and the other is to go out to there. What are those distances? This one, because we're talking about the major or longer axis of the ellipse. This one, I got to figure out a way to refer to that. But I put a brace. That's the semi-major axis. Well, we call it a semi-major axis actually, but it's the semi-major. My brain is just shut down. I can't think of what we refer to the length as. Anybody? Can anyone help me? Semi-major axis has a. Okay, it's the semi-major thing. We'll go with that. Jigger. Right. And then there's also this, because it's half of the major thingy. We've also got the semi-minor length. That would be this one. And there are various approaches one can take, but what Kepler decided to use was just that one. Use the semi-major length. Right? And that is an approximation of the radius of the ellipse. Because of what he was doing was just about proportions, it kind of didn't matter. He could have used the other one. He probably could have used like the nearest approach or the farthest approach from the sun, because again, it's about proportions, and all of these things would have been proportionate. But his third law is that the period and this thing satisfy a power law. So number 3, the period and the semi-major axis, the semi-major thingy, let's just say semi-major distance. I'm going to call it R because I think of this as like a radius for the ellipse. Satisfy a power law. Some constant times R to the 3 halves. Or maybe it's 2/3. This is the part where I forget. Is it 3 halves or 2/3? So we can Google is our friend. Let's find out. I'm going to do the right thing.
3 halves.
Oh, you gotta look up what the semi-major thing is.
So we are so bad. It was Kepler's third law.
It's 3 halves.
The square of the period is proportional to the cube of the semi-major axis. They just call it the semi-major axis. I want the length of the semi-major axis here. So did I do this right? If I say r to the 3 halves, like square both sides, and you get the p squared is a k, it's a different k, but it's okay, times r to the 3. That's the way they've stated it. Do I have it right that it's the square of the period is the cube of the semi-major axis? Okay. So what that does is it tells you really about how much area is being swept out by these lines to different planets. It's not saying any particular, it's not saying one rule, it's saying a bunch of rules. For each orbiting body, there's a proportionality between its period and how far it is from the sun. Does that make sense? Which ones take longer to go around, the inner planets or the outer planets? Longer. Yeah. Outer planets, like Pluto, takes hundreds of years to go around the sun. The Earth is just 1 year. Jupiter is like 6. Which is? I think it's 88. 88 days. That's a short year. So does this relationship we've been talking about make sense relative to what we said? If R is smaller, what should happen to P when we raise it to the 3 halves power? What does a 3 halves power law curve look like?
Well, it's not like
This one's the answer.
It kind of looks like half of a parabola, but not really. So it's definitely, you see the proportionality that if you increase the radius, the period goes up, go higher, even longer. Okay, good. But it actually, the fact that it's curved the way it is tells you something kind of interesting. The outer planets have extra longer years. It's not just about their radius, it's this 3 halves power of the radius. So there's a sort of a magnifying effect of going out like that. If you go out twice as far, you go nearly 3 times as long. Here. So that's Kepler's third law. Now that was really big stuff. And with this material, you wanted me to look up something else? What was it?
oh, the semi-major thing. Though the Google search wasn't super.
It does just refer to it in here as the semi-major axis, which to me is the actual axis that's outlined, not the length there. is seeing it the same way, and that's in Wikipedia, which is always right.
I've only ever heard of the semi-major axis as well.
Maybe my brain is just failing in a different way. It's thinking that there's another name for it when there isn't.
So wasn't there something for physics? I'm not
Oh,
very
wouldn't you call
good.
this physics?
Well, 'cause I've never studied physics before, so I was like, I think his name sounded familiar with physics.
The thing is, he's at about the time when math became math and not everything else that the Pythagoreans had counted as math. So up until then, astronomy was just a branch of math. And so that's probably why the Holy Roman Empire thought, okay, he's fine, he's the mathematician, because he was an astronomer, and that's part of that. Now we sort of told astronomers to get out and go play with the physicists, but they still do some good math.
They still count.
They still count a little bit. There's theoretical astronomers, right? Theoretical physicists like Stephen Hawking. I mean, Stephen Hawking is a way better mathematician than I'll ever be, but he really considers himself a physicist. What are you going to do? To tell us that. At the moment?
You have a light bulb.
Yeah, I know. I was like, I heard it go off.
She's not sharing her light bulb moment with us.
I was thinking of like the observatory, the Yale Observatory for the telescope.
The old one that's up on the hill?
Yeah,
Yeah.
not that.
That's like 150 years old. Well, there's a new building there where they have a planetarium for they do kid shows and stuff. If you ever get the chance, go up to Science Hill on Tuesday evening. They show you a cool little movie, and then they let you go out and use some telescopes and actually look at stuff. And then you can also see one of their ancient refractor telescopes is on display. It's this gorgeous brass and metal construction that it's beautifully ornamented. And the mirror, it's not a mirror, it's a lens. It's about that big. You could buy that for your kid today. But this was the best research telescope in the world. Okay, so we talked about his laws of planetary motion, but he didn't just leave it there. So this was a theological argument versus principle. Kepler, while he was very devout, he loved the Copernican system. He thought that was the obvious and clearest and simplest way for the universe to be constructed. There's a tool actually in critical thinking and logic known as Occam's razor. Have you heard of Occam's razor? Yeah. It can be stated in multiple ways, but my favorite is if you've got competing explanations for something, and one is simpler than the other, it's probably the simple one. If you have to add epicycles to your cycles and then epicycles on your epicycles, that's probably not the real way. They just move in ellipses. That's a lot cleaner. Although it didn't seem compelling to people who believed that God had to deal with circles. But I mean, that's a certain kind of hubris that you imagine what God has to do, and you're like limiting his options at creation to what you think he should do. Kepler, while he was very devout, didn't put any kind of constraints on the Creator. He said, yeah, if he wanted to make it with ellipses, he could do that. Which, obviously we're modern people. We think about this stuff differently, but I'm all down with Kepler. I'm not personally a deist, but I can see that point of view makes sense. So we've got this problem that half the world believes in the Copernican system, and 1% of the world believes in the Copernican system. 1% believes in the Aristotelian system from way back, with the Earth at the center of the universe. And 98% of the people couldn't give a shit. That's really where we're at. But a lot of the people who did care were the higher-ups in the Catholic Church. So they tended to get angry with people that proposed the Copernican idea. And that's what happened to Kepler. He got excommunicated. He was a Protestant, so they threw him out of his church for propounding this idea. And it really hurt him because he was very devout. He spent a lot of the end of his life trying to get back in, coming out of the cold. They wouldn't take him back. To prove that his theory, the Copernican system with these modifications, was correct, he created tables that predicted the future motion of the planets. And people had done this before with their epicyclic models too. And the tables always kind of eventually got out of sync because the real planets weren't following the paths that these perfect circles with epicycles were. And in fact, it didn't take very long. A year or two would be enough for the planetary motion to no longer be doing what the epicycle tables said they were, especially for the inner planets of Mercury and Venus. But Kepler's tables were like clockwork. There was no straying. He had it nailed down. And in fact, they're probably good today. They're probably good as far as naked eye observation is concerned. You can probably get the planets to closer positions now with instruments. And this was powerful evidence now for the Copernican/Keplerian view. So yeah, eventually they did get convinced. But it was after Kepler was dead, so he never did get back to his church. All right, so that's the end of Wednesday's slides. To get today's slides.
Have accepted it back in even after he said, if he believed in that, they probably would have let him rest in peace.
I don't think it would matter who the dead guy was.
Well, if it was his belief and he has the right belief, then it would matter to him because it would
That's true.
It would fly
It's
off.
a version of Pascal's wave theory.
I don't believe it, but that's not my.
I'm with you there. I think that you made a valid point.
It was only in the 90s when the Catholic Church forgave Galileo. Maybe his church will in due time.
Oh.
We should look it up, see if anybody can find out whether Kepler has ever recommunicated with us or not.
What church was the one?
It was Luther. Some Protestants. So let's talk about our remaining time together first. Counting today, we have 14 remaining weeks. I'm sad. Because I enjoy our time together. And I have made a list with 14 mathematicians that we have to discuss. I have a list with 32 names on it, but there's 14. I called my list down to the point where, okay, if we just get these people, I'm going to be happy.
One a day.
There's one a day, exactly. Here's the list. Fermat. I don't know whether it's pronounced Fermat or Fermat, but I'm going to pretend like I speak French and say Fermat. I'm sneaking Newton and Leibniz together into one class because it's really about both of them thought they had calculus down, and both of them thought they invented it, and then they had a fight with no swords, which is nice. There were 8 guys named Bernoulli. I'm going to treat the whole family in one day. So you see, I'm kind of cheating with it. Okay. Leonhard Euler, the most famous Swiss person of all time. Okay. He's actually on the money in Switzerland, except now they have euros, but he was on the money in Switzerland. Another thing where I'm going to sneak something in, the Napoleonic era in France, he had 3 guys he called his mathematical generals. And Lagrange, Laplace, and Legendre were all important mathematicians. You should see that their ages are the 2 younger guys born about, 3 years apart? 1750, and then another guy about 14 years older than that, 36. So he was the old man, and the other guys were kids. They did a lot of really important math at that time. One thing extra mathematical that he did, one of the things Napoleon got into was conquest of parts of Africa, Egypt in particular. It was his soldiers that shot the nose off the Sphinx. You know that? I'm really annoyed with them for that. They were just using the Sphinx for target practice. Jerks. Really. But one of the positive outcomes of Napoleonic conquest of Africa is he set up an educational system in northern Africa for the people that lived there. These guys designed it. So it became the model for French education as well. And it was good. There's still a lot of countries in Africa where this was because of this. So it was colonialism, but there was some good sides to it. Sophie Germain, born in the year the U.S. was formed, I gotta say she's the first officially female mathematician that we can know for sure what she did. Like from Hypatia from ancient Greece, they call her the first female mathematician, but A, there's precedent for there were females in the Pythagorean movement, and B, nobody knows quite what she did. They say she studied conic sections, but there's not a lot of written records of what she did. Sophie Germain, we know what she did, and it was awesome, impressive mathematics. So it's not her. Gauss, everybody's heard of Gauss, I hope?
Yeah.
Carl Gauss.
Little Gauss.
CF, Carl Friedrich Gauss. So if you do magnetism in physics, the units of magnetism are Gauss. Unless you're dealing with really, really, really potent magnetic fields, and then they call them Teslas. I think it's like 1 million Gauss to the Tesla. You have to go to like an MRI before you see Tesla fields.
No, so actually Gauss related in linear algebra.
In what?
In linear algebra.
Oh yes. Famous story about Gauss. He invented the method of least squares probability, which he solved by linear algebra, in order to locate the planet series, the minor planet series. It was funny. These guys had observed Ceres, which is actually an asteroid, but it's nearly as big as our moon, so it's not a small asteroid. It's basically a planet in its own right. And yet they observed it, tracked it for a few days, and then it was cloudy, and they lost it, and they couldn't find it again. So they're like, shit, get Gauss on the phone, he'll figure this out for us. He was able to compute the orbital elements of Ceres and extrapolate the most likely path for its orbit and said, okay, look for it here. And to do that, he had to invent new mathematics. He did it overnight. The method of least squares that we talk about to find a regression line that fits data, that's what he created overnight in order to solve this problem. And sure enough, when they looked where Gauss had told them to, they Ceres again. Gauss is pretty awesome. Hamilton is one of my favorite guys. He's the first person to, he did a lot of neat stuff in discrete math, which is my area. My favorite thing about Hamilton is an object lesson in stick-to-itiveness. He decided, you know about complex numbers where you can have a real and an imaginary part, and so for pairs of numbers, pairs of real numbers, there's a way to think about them as a single entity, and you can multiply and divide and add, subtract these single entities. Hamilton said, well, I'd like to do that for 3Ds. I'd like to be able to take a point in space and think of that X, Y, and Z as being a real and an imaginary and another imaginary. So he wanted to sort of get a way to multiply points in space, vectors. And he worked for 10 years at this problem. I love this. Every night, he'd come down from working in his office all day long, and his office was in the home, and his kids would be like, well, Daddy, have you figured out a way to multiply triples yet? No. Don't bother. But 10 years later, he did it. He got so excited, he went out and carved it on a bridge. He was Irish. Possibly the most romantic story of all of mathematics is the tale of Galois. So he's in the other French Revolution. The one where they were cutting everybody's heads off real fast. He fought a duel. Can you see how old he was from those birth and death dates? 21. Shot in the stomach in a duel over the honor of a lady, but it was really a political assassination, apparently. They just didn't like this action.
Yu-Gi-Oh duel?
Sorry?
Yu-Gi-Oh duel?
It was the kind with pistols, and you walk away 20 paces and turn, and both of you die.
It's not a children's cartoon. It wasn't a children's.
No, it wasn't, but you could do it that way. It would be better. I would prefer they just cut his nose off, to be honest. Because, at the age of 21, he had done such amazing math that some of you are in abstract algebra and are complaining about abstract algebra. He did this thing called Galois theory, which, if we were lived in a perfect world, would be the final cap on your abstract algebra experience. You would learn a little bit of Galois theory. But at 21, he had completely mastered the abstract algebra that's troubling you, and with this.
It's not making me feel dumb.
No, look, it's freaking genius. I mean, don't feel dumb if you're compared to Galois. I'm just trying to point out he was awesome. Yeah, so.
So he's the reason for the pain and suffering.
So no, he's the cap on top of it.
He's the reason to. Okay, so you guys know the quadratic formula? You know that we didn't talk about it, but in like the 1400s, somebody came up with a formula for the cubic, and you're able to solve a cubic in radicals if you want. Of course, there's 3 solutions for a cubic instead of 2. The quadratic formula, we can all memorize it, no problem. The cubic formula, I don't think anybody has ever memorized. It's literally about a paragraph. And then, about another 100 years later, somebody figured out the 4th degree equation. There's 4 solutions for that in general. So you've got 5 coefficients, A, B, C, D, and E, and you can write down a formula, solving it in radicals. Galois was interested in the general question of finding the formula for the last one, the quantic equation, is about 4 pages long. It's a crazy long set of formulas. But Galois was, what's the general thing? If you give me any equation, maybe it's degree 17, how can I come up with the solution of that polynomial equation using radicals?
And he found it?
No. But he set up the theoretical structure, and it's all about abstract algebra. There's actually groups involved. The simplest group is the one for complex numbers. You know how when you have the zeros of a polynomial, you either get real zeros or you get pairs of complex conjugates? Well, here's the group. You can switch things. You can permute the complex conjugate pairs.
Okay.
When you've got a degree 5 thing, it may have a real root and then 2 pairs of complex conjugates. And you can switch this one, or you can switch this one, or you can switch them both. That's a group. Those are permutations I'm describing by finger my fingers. So he came up with a connection between solutions of polynomial equations and group theory. And later people took that and realized the 5th degree and higher can't even be done. So there's features of the groups that tell you you can't solve those equations. Ada Lovelace is the first computer scientist, and actually daughter of Lord Byron, so she's pretty a huge spot to look at. George Cantor is the first person to realize infinity comes in more than one flavor.
Oh, I know about that.
Yeah, it's cool.
Yeah.
So we got to do that.
Yeah.
From after this class, after day 10, we're going to be going, well, if somebody says something is infinite, we go, which infinite? You're going to pull that on people because they'll be like, what do you mean, infinity is infinity? No, I'm sorry. So that'll be fun. Sophie Pavlovskaya, I'm going to have to look up her accomplishments. She's quite famous. There are people who have celebrations about her birthday. So I know she's famous. I don't know what she worked in. But that I'm going to have to look up. Emmy Noether is another female mathematician. Note. It's a joke because her name is pronounced Noether in German. She did abstract algebra and in particular ring theory. So those of you in abstract started talking about rings. Did they ever mention Noetherian rings?
I don't think so.
So there's
definitions.
some rings have a special structure where the ideals can be always decomposed into what are called descending chains. And that's called Noetherian, so that's named after her. That's what she's studying. And again, actually, that has connections to this idea of finding solutions to higher degree polynomial equations. And finally, Alan Turing. Who watched The Imitation Game on the show? Okay, so I would say that I am alive today because of this man. Literally. He was responsible for ending World War II significantly earlier than it would have gone if it had just been a knockdown, drag-out fight all the way. His program to break Nazi codes was the first major application of mathematics to warfare. So before that we had the bones, Napier's bones let us figure out how to shoot people with our cannons quickly.
The thing with like matchboxes where if you type a random letter appears and you can appears letters.
It sounds like you're describing a cipher, which is definitely a kind of thing here, but There was this machine-driven cipher that the Germans were using. They used a device called the Enigma. The Enigma machine was a cipher on top of a cipher on top of another cipher with 5 layers of permuting stuff. It was polyalphabetic, meaning you didn't just turn, like, an easy cipher is take A and turn it into C. And then B will turn into D. You just shift all the letters down, that's an easy cipher. This cipher would have said, if you happen to see the sequence P, Q, Z, W, that'll get transformed into A, R, S, V, for instance. So they had a machine that would do this, and it was incredibly complex. But the British set up a code breaking station, and they trained all these ladies to listen to the radios and listen for, this was Morse code, right? The Germans would send out messages in Morse code over the radio. Women ended up being able to recognize the operator. It's very interesting. They called it a man's fist. His fist was, after listening to different people sending stuff for a while, you realize that different people had like a different amount of gap between the letters. Or they always make their A's by going dash dot rather than dash dot. There'd be some subtle thing that you would let you detect who was sending, and they had nicknames for all. Right? So that was extra information that the movie didn't mention all this. But the code listeners could transcribe all the messages that were sent and give this extra information, and they would put it all into Alan Turing's code-breaking computer, one of the first computers. And often they were able to break the code sometime during the same day that the message was sent.
Actually, the code, the keystroke patterns you're talking about, they actually use that today as biometrics. They're actually considering adding as.
I've actually there's a couple of students at Southern that were trying to use that as a way to identify people on cell phones. Like you can just say, you have a certain task to do, and you sweep your finger through these 4 points, and there's enough variability in the way different people will do that task that you can tell who's who. But it's very similar to it. Anyway, Turing is our last guy, and I've run out of time to talk about Fermat, but let me show you a picture. There he is in his older years. He kind of got a wheeze, it looks like. Not as many chins as I do. They called him the Prince of Amateurs because he was actually an attorney. He was really a lawyer. But he did some amazing stuff. And I guess I'll end today by mentioning this. After he was dead, his son was going through his stuff, and he found a copy of Diophantus, the ancient Greek. We talked about a lot of things like x squared plus y squared equals z squared, the Pythagorean triples. Diophantus apparently considered that equation, and was, well, maybe not, anyway. Fermat's son found this copy of Diophantus, which is translated into Latin. Right? So we have a Greek writer in Latin, and so Fermat, in the margin of this book, wrote this note that said, yeah, but if 2 is any bigger number, you can't find integer solutions at all, except for the trivial ones. Like you could have, 0 cubed plus 1 cubed equals 1 cubed. You just trivial ones like that. But you can't find the interesting solutions like 3 squared plus 4 squared equals 5 squared. And he wrote in the margin that he had a demonstration miraculous. There's a miraculous proof of this. And that's what, and then he was dead, so nobody knew what he was talking about. Yet he was the Prince of Amateurs, so they thought, well, maybe he had something. 300 years people beat their heads on this problem. And finally it cracked in 1993 with an argument that certainly was not what Fermat had. It was a very modern proof, but a lot of really interesting mathematics got spawned by people trying to kill this problem. So I'll talk about that a little more next time. Fermat's last theorem.